Voyager 2's data complicates Voyager 1's famous stagnation region. In November of 2019, NASA published 5 peer-reviewed papers at once, each one describing a different instrument's view of Voyager 2's crossing into interstellar space a year earlier. Buried among the headline results was something quieter, and in its own way far stranger. Data that didn't just add a new discovery to the mission's record, it started quietly unraveling one of Voyager's most famous prior discoveries instead. For nearly a decade, scientists had confidently described a bizarre region at the edge of the solar system, where the solar wind simply stopped moving. Voyager 2's new data suggested that description might not have been telling the whole story. This is what NASA confirmed Voyager 2 sent back that nobody was fully prepared for, and why it's forced researchers to re-examine one of the mission's most celebrated findings. Both spacecraft launched within weeks of each other in 1977, riding a rare planetary alignment that let a single probe use the gravity of each outer planet to slingshot toward the next one. Voyager 2 went on to become the only spacecraft in history to fly past all 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, while Voyager 1 took a faster, more direct route past Jupiter and Saturn before angling sharply upward out of the plane the planets orbit in, aimed toward the very edge of the sun's influence. Picture both spacecraft today, more than 4 decades and billions of miles removed from that shared launch pad, moving outward in almost opposite directions, each one carrying a small gold-plated phonograph record and a set of scientific instruments that have long since outlived every projection their original engineers ever made for them. To understand why this particular contradiction matters, you have to go back to 2010, when Voyager 1, still years away from actually crossing into interstellar space, reported something nobody expected to see. Voyager 1's plasma instrument, the one instrument best suited to directly measure the speed and behavior of the solar wind, the constant outward stream of charged particles blown off the sun, had already failed back in 1980, more than 3 decades earlier. Without it, mission scientists had to infer the solar wind's behavior indirectly, using a completely different instrument called the low-energy charged particle detector, measuring how fast energetic particles were striking the spacecraft from different directions and mathematically working backward to estimate the underlying wind speed. Using that technique, researchers watched the outward speed of the solar wind steadily decline for years, dropping at a rate of roughly 20 kilometers per second annually, until, in June of 2010, it appeared to hit exactly 0 and simply stay there. That result stunned the scientists studying it. Rob Decker, a co-investigator on the instrument responsible for the finding, described his own reaction to seeing the readings come in. After 33 years of Voyager acting as a reliable workhorse, watching the numbers settle into solid zeros felt like the spacecraft was showing them something completely new all over again. Nobody had expected the solar wind to behave that way, at this particular boundary. The prevailing model predicted the wind should gradually turn sideways as it felt the pressure of the surrounding interstellar medium pushing back against it, curving off at an angle rather than breaking to a dead stop, the way a river bends around an obstacle rather than simply piling up motionless against it. Instead, Voyager 1's data described something researchers started calling a stagnation region, a strange, becalmed pocket at the edge of the solar system where the outward flow of charged particles from the sun appeared to simply halt entirely, the cosmic equivalent of sailing into a patch of ocean with no wind at all, a region scientists began comparing to Earth's own doldrums, the notoriously still equatorial band of ocean where sailing ships could sit motionless for days, waiting for wind that never came. Ed Stone, the mission's longtime project scientist, described it at the time as Voyager, showing that whatever lies outside the solar system was genuinely pushing back. The magnetometer data seemed to back up the story. Over roughly the same stretch of time, the solar wind speed was falling toward 0. Voyager 1's instruments recorded the surrounding magnetic field intensity doubling, exactly what you'd expect if incoming pressure from beyond the solar system were compressing everything at the boundary. Together, the way cars pile up bumper to bumper at a clogged highway off-ramp. Between the vanishing wind speed and the strengthening magnetic field, the stagnation region became one of the most widely reported findings of Voyager's entire post-planetary mission, described in NASA press briefings, textbooks, and popular science coverage as a genuine, confirmed feature of the solar system's outer boundary, a strange, calm doldrum zone Voyager 1 had to sail through before finally breaking through to true interstellar space in 2012. There was just one problem, and it's the exact problem Voyager 2's 2018 crossing ended up exposing. Voyager 1's plasma instrument had been dead for 30 years by the time any of this happened, meaning every single stagnation region measurement came from that same indirect method, deriving wind speed mathematically from charged particle data rather than measuring it directly. To pin down the technique even further, mission engineers occasionally rolled the entire spacecraft, a slow, deliberate 70-degree rotation held in a careful, gyroscope-controlled orientation, a maneuver Voyager 1 hadn't performed in over 2 decades, specifically to calibrate its magnetometer and squeeze an extra dimension of directional data out of the charged particle readings. Nobody had an independent way to double-check whether that entire indirect technique was actually reliable at these extreme distances in the specific, unprecedented environment nobody had ever sampled before. Voyager 2 changed that, because unlike its twin, Voyager 2's plasma instrument was still fully functional as it approached its own heliopause crossing 6 years later, giving scientists something they'd never had for Voyager. 1. A direct ground truth measurement of the solar wind's actual speed to compare against the same indirect calculation method. The comparison didn't go the way anyone expected. As Voyager 2 approached its own crossing, its directly measured plasma speed, read straight off its working plasma instrument, stayed comparatively steady for most of the approach, only dropping toward zero very close to the heliopause itself. Nothing like the long, gradual, years-long stagnation Voyager 1's indirect data had implied. Meanwhile, the same charged particle-based technique that had produced Voyager 1's famous zero-velocity readings, when applied in parallel to Voyager 2's own charged particle data, often disagreed substantially with what Voyager 2's plasma instrument was measuring directly, sometimes estimating speeds significantly higher than the true value, sometimes significantly lower, with no clear, consistent pattern to the errors. A follow-up analysis, published in the Astrophysical Journal, and built around a new technique for extracting additional information from Voyager 2's charged particle data, confirmed the mismatch explicitly, describing the differences between the indirect estimates and the direct plasma readings as simply not expected and not yet explained. Sit with what that actually means for a moment, because it's a more unsettling result than it might initially sound. It doesn't necessarily mean the sun's solar wind never slows down dramatically at the edge of the heliosphere. It means the primary tool used to measure that slowdown for Voyager 1, the only spacecraft where researchers had ever tried it, produced numbers that, when finally checked against a working plasma instrument on a second spacecraft, didn't reliably match reality. Researchers studying the discrepancy have floated a specific possible explanation: that oxygen ions, heavier, slower-moving charged particles than the light hydrogen ions. The instrument was originally calibrated to track, may have been leaking into the charged particle detector and contaminating its readings, subtly throwing off the derived wind speed without anyone realizing it at the time, since the instrument had no independent way to distinguish which type of particle it was actually counting during those critical years. That would mean one of the most famous, most widely reported discoveries to come out of Voyager's decade-long approach to interstellar space, an entire named region of space that made it into science. Documentaries and museum exhibits might have been shaped, at least in part, by an unnoticed instrumental artifact, rather than purely by the physical behavior of the solar wind itself. To be clear about where the science actually stands today, this isn't a case of researchers throwing out the stagnation region entirely and admitting Voyager 1 was simply wrong. It's messier and more honest than that. The magnetic field doubling that Voyager 1 recorded during the same period remains a real, independently measured result, using an entirely different instrument than the one now under scrutiny, and that finding still needs an explanation regardless of what happens to the wind speed story. What's changed is the confidence with which scientists can describe exactly what was happening to the solar wind's velocity during that stretch, because the one tool used to measure it has now been shown, through direct comparison on a second spacecraft, to sometimes produce numbers that don't match a working plasma instrument's ground truth. Ongoing modeling work, including detailed numerical simulations published as recently as February of 2026, that attempt to recreate the entire boundary region using physics-based models running on high-performance computing clusters, is still actively trying to reconcile these competing pictures, incorporating both, rather than treating either one as the default correct answer, still treating the region as a genuinely open question in heliophysics, rather than a settled textbook result nearly a decade and a half after Voyager 1 first raised it. That wasn't the only place Voyager 2 delivered data that ran against expectations during its own crossing. Perhaps the most quietly remarkable result had nothing to do with wind speed at all, and everything to do with simple geometry. Voyager 1 crossed the heliopause in 2012 during a period of relatively high solar activity, when the sun's magnetic output was strong, and its solar wind was, broadly speaking, pushing outward with more force. Voyager 2 crossed a completely different section of the boundary years later, during a period of comparatively low solar activity on the opposite side of the sun's roughly 11-year cycle, when that outward pressure should have eased considerably. Scientists expected the heliopause to behave something like a lung, expanding outward when the sun is more active and its solar wind pushes harder, contracting inward when solar activity quiets down and that pressure relaxes, the entire bubble breathing in and out over the course of each roughly decade-long cycle. Given that both spacecraft crossed at such different points in that cycle, years apart and on opposite sides of the sun's activity swing, researchers genuinely expected to find them exiting at noticeably different distances. From the sun, the bubble caught mid-exhale for one crossing and mid-inhale for the other. Instead, Voyager 1 crossed at 121.6 astronomical units, and Voyager 2 crossed at 119, a difference of less than 3 astronomical units despite years of separation and opposite phases of solar activity. Stamateos Krimigis, a longtime Voyager instrument lead at Johns Hopkins, called this similarity very strange, precisely because the underlying model predicting a breathing, expanding, and contracting boundary should have produced a much larger gap between the two crossing points than what actually showed up in the data. Whatever mechanism actually governs the size of the heliosphere, it apparently isn't responding to the solar cycle the simple, intuitive way scientists had assumed it would for decades. Voyager 2's magnetometer delivered its own separate surprise, this one concerning the strength, rather than the timing, of the boundary it crossed. Once fully into interstellar space, Voyager 1 had measured a surrounding magnetic field of roughly 5 microgauss, itself already about twice as strong as pre-crossing models had predicted, a field so faint by everyday standards that it's still tens of thousands of times weaker than Earth's own magnetic field at the surface, yet strong enough, at that distance, to noticeably deflect and organize an entire ocean of interstellar particles. When Voyager 2 made its own independent measurement 6 years later at a completely different point along the heliosphere's surface, it recorded an even stronger field around 7 microgauss. Krimigis described the effect of that unexpectedly powerful surrounding field in blunt terms, comparing the pressure of the interstellar magnetic field pressing in on the heliosphere to a kind of straitjacket, squeezing the sun's bubble from the outside with considerably more force than any model built before Voyager 1's crossing had accounted for. A squeeze strong enough that some researchers now believe it plays a direct role in shaping the heliosphere's overall size and structure, rather than being a minor, secondary detail layered on top of a boundary primarily controlled by the solar wind's own outward pressure alone. There's one more thread to this story that's still actively unfolding today, years after both crossings, and it concerns the density of the plasma each spacecraft is currently moving through. Both Voyagers can measure interstellar electron density indirectly by detecting radio emissions produced when solar eruptions cause electrons in the surrounding plasma to oscillate, essentially eavesdropping on the sound of distant solar activity rattling the interstellar medium itself, the way a struck tuning fork rings at a specific pitch determined by its size. Don Gurnett, the scientist who led that plasma wave work for decades, has noted that measurements taken well after each spacecraft's initial crossing show the surrounding interstellar density has continued climbing higher than what either spacecraft first measured immediately after breaking through the heliopause, a trend that has continued long enough and consistently enough that researchers expect it to keep generating fresh data as the sun's activity ramps toward its own next peak. Asked what might happen next, Gurnett offered an informed guess rather than a confirmed answer, that the density might be expected to reach some kind of peak before eventually settling back down somewhat, speculating that interstellar material could be quietly piling up against the outside of the heliosphere the way snow banks up in front of a slow-moving snowplow, compressed and accumulating right at the boundary where the sun's bubble pushes back against the surrounding galaxy. Nobody currently knows for certain whether that prediction will hold, which means both spacecraft are, in effect, still actively testing it in real time with every new reading that arrives. Taken all together, what Voyager 2 actually confirmed wasn't a single, tidy new discovery. It was something more valuable and considerably messier. The first real opportunity to check one spacecraft's decade of celebrated findings against an independent second dataset collected under different conditions, at a different location, using a still-functioning instrument its twin no longer had. In science, that kind of cross-check is exactly how genuine progress gets made. Not by adding new mysteries on top of settled answers, but by discovering that some of yesterday's settled answers weren't quite as settled as they seemed the first time around. All of this scientific back and forth is unfolding against a hard, ticking deadline that has nothing to do with the physics itself and everything to do with the hardware collecting it. Both Voyagers run on radioisotope thermoelectric generators, converting the steady decay of onboard plutonium into electricity, and that power supply has been fading gradually and permanently every single year since launch. Engineers have already had to power down instrument after instrument across both spacecraft simply to keep the remaining ones alive a little longer. And mission teams have said openly that within the next few years, the available power will finally drop below what even a single surviving instrument needs to keep functioning at all. That means the specific instruments responsible for this entire unresolved contradiction, Voyager 2's still functioning plasma detector chief among them, are running on borrowed time. Every additional year of directly measured plasma data adds to a data set that will likely never be replicated again in most of our lifetimes, since no other spacecraft is currently positioned to reach a comparable distance with a working plasma instrument anytime in the foreseeable future. So here's where that leaves things today. Voyager 1's famous stagnation region hasn't been erased from the scientific record, but it can no longer be described with the same simple confidence it once was, precisely. Because the only spacecraft capable of checking the method behind it found that method didn't reliably agree with direct measurement. The heliopause itself turned out to sit at nearly the same distance from the Sun, regardless of where in the solar cycle each spacecraft happened to cross it, defying the breathing boundary model researchers had built their expectations around. The interstellar magnetic field turned out to be stronger at both crossing points than anyone predicted, squeezing the solar system from outside with more force than any pre-Voyager model accounted for. And the density of the plasma surrounding both spacecraft is still, right now, continuing to climb in ways nobody can yet say for certain when or whether it will level off. None of that adds up to a single, clean answer about what the edge of the solar system actually is. It adds up to something more honest and, in its own way, more valuable. 2 independent, half-century-old spacecraft, launched before almost anyone alive today was born, still returning data precise enough to force working scientists back to their own decade-old conclusions, and precise enough to reveal, again and again, just how much about our own solar system's true boundary remains genuinely unresolved. Think about what that actually requires from the field of heliophysics as a whole. It would have been easy in 2012 to simply accept Voyager 1's stagnation region as a settled, permanent addition to the textbooks, close the chapter, and move on to studying whatever came next. Instead, when a second spacecraft finally arrived at the same generals boundary with a different set of working instruments, researchers didn't quietly bury the contradiction or explain it away to protect an already celebrated result. They published it in detail in a peer-reviewed journal, explicitly describing the mismatch as something not yet understood, an admission that the earlier finding needs more scrutiny rather than less. That's not a failure of the mission. It's closer to what scientific progress actually looks like in practice, messier and less telegenic than a single, permanent discovery, but considerably more honest about where genuine uncertainty still remains. Somewhere more than 11 billion miles from Earth, Voyager 2 is still moving outward. Tonight, still measuring the plasma around it directly, still quietly checking its twin's homework from a decade earlier, one carefully transmitted data point at a time, using a plasma instrument that has now outlasted every prediction ever made about its working lifespan. Whatever it sends back next, whether it resolves the stagnation region question once and for all, or simply adds another layer of complication on top of everything that's already unresolved, will very likely need to be recorded, analyzed, and cross-checked within the next handful of years before the last of its power finally runs out. And this particular conversation between 2 aging spacecraft, still correcting each other from opposite sides of the solar system, goes quiet for good.